Howdy folks, this discussion is going to be all about modeling with Dirac Delta functions, particularly in electricity and magnetism, or E&M for short. I recently did a discussion just on Dirac Delta functions more broadly. It can be found linked in the description. If you need a refresher, you want to check that out. Let's dive into modeling with Dirac Delta functions in E&M. And we're going to start off with the simplest possible scenario, which is just a single point charge right at the origin in 3 dimensions. It's going to be a point charge Q, and again right at the origin, so our vector representing the position of this point charge is just going to be 0x hat, 0y hat, 0z hat. In modeling out the charge density then, all of the charge of this system is localized to one specific point within our 3 dimensions here. It's right at the origin. One small step off the origin in any dimension will yield no charge. So how do we localize all of that charge just to one specific point? Well, we do that with Dirac Delta functions. To model our charge density, you're just going to have our charge Q multiplied by a 3-dimensional Dirac Delta function centered at, in this case, 0, but if this was just some general R, you could say R0, it would just be centered at R0. And what this does is it allows our charge to just strictly be localized right at that origin, or right wherever that 3-dimensional Dirac Delta function is centered at. So if, say, for example, we wanted to get the total charge, we would just integrate our charge density over all space, which, if we expand it all the way out, would just be integrating Q times delta x, delta y, delta z, dx, dy, dz. Since Q is a constant, that goes out in front, so it's just Q times 1 times 1 times 1. So the total charge of this entire system is Q, as you would otherwise expect. And that's what makes the sifting property of the Dirac Delta function really awesome as well, is that computing things like total charge is just a matter of counting up the total charge within the bounds of your integration, because all those point charges are going to be localized to wherever the respective charges are centered at with those delta functions. So if we consider a system of multiple point charges, let's say that we have 3 of them here. We have Q1, Q2, and Q3. Q1 is centered at R1, Q2 is centered at R2, and Q3 is centered at, of course, R3. Then modeling out the charge density would just be Q1 multiplied by a Dirac Delta function centered at R1, plus Q2 times a Dirac Delta function centered at R2, or a 3-dimensional Dirac Delta function centered at R2, and then the same thing for R3 respectively. Total charge, again, would just be integrating this thing over all space, and all of that charge for each one of those point charges is isolated to the specific points in which those delta functions are centered at. Now remember that in the real world, not everything is always over all space. But say, for example, that we start working in, let's say, a plane, and for our system of 3-point charges, let's say that Q3 doesn't fit within that plane, you wouldn't count that when you're doing your integration. Or in other words, it wouldn't fall within the bounds of integration, so it wouldn't be added in the total charge. And again, this is the real utility of the Dirac Delta functions. It centers our point charges to specific points where if we just go one small tiny little epsilon off of that point, there is no charge. And with the use of the Dirac Delta function sifting property, it's just then a matter of looking at what our bounds are and counting up all of the charges that fit within those bounds and adding them all together. So let's say we bump this up a little bit from point charges to some type of shape. And the simplest shape that we might think about when it comes to E&M is like a wire, so a line of charge. You can still model these with Dirac Delta functions, and it's actually really convenient to model these with Dirac Delta functions. We'll say that, our line of charge has some linear charge lambda, okay? So modeling out charge density would be lambda times wherever we want this localized. If we have our line of charge here running along our z-axis, we have charge everywhere in z, so would it be appropriate to put a delta function there if we're trying to model one specific point? No, of course not, because charge is everywhere along our z-axis or in our z-dimension. We need to localize it, though, for x and y, though. we don't have any charge anywhere off of x equals 0 and y equals 0, because it's running along our z-axis. So it would just be, so modeling out charge density would just be lambda times delta x centered at 0 and delta y centered at 0. Now, what do we know about lines of charge? Well, it's most likely going to be used to model like a wire or something like that, okay? And wires are finite. So integrating this whole thing, we could do negative infinity to infinity for our x and our y dimensions, but for our z dimension, let's say that this is a wire of finite length L, so we could integrate from 0 to L, and you would just get lambda L as your total charge after integrating all this. And this just makes it really simple and straightforward based off of the sifting property of the Dirac Delta functions. And that's what's so useful here. You could almost think of the Dirac Delta functions, or integrating those Dirac Delta functions, as kind of collapsing everything to one specific point in whatever the dimension is where you're centering that Dirac Delta function. And so if we bump this up for one more scenario, and now try to model an infinite plane, let's say. So let's say that we have that plane just in the xy plane. We have a consistent charge, sigma, all throughout our plane, our xy plane. The way that you would model this is just sigma times a Dirac Delta function for z centered at 0, because it would just be the plane at z equals 0. You could, of course, shift it up or shift it down, but you see what I'm getting at when I say that these Dirac Delta functions, and integrating them, it localizes things to one specific point in whichever dimension you're working in. So then again, in this scenario, to get the total charge, you integrate your charge density. dz is just going to give you a 1, and so it's just going to be sigma then times integrating dx and dy, so it's just going to be sigma times the area of whatever that plane is, depending on whatever your domain or bounds of integration are. And so that's the best way to think about modeling with these Dirac Delta functions, is just think about where you want to center things at. Where should stuff only exist in one specific point? That's why with point charges, they're so incredibly useful, because you need to localize all of that charge to one specific point. If you just step one little epsilon off of that point, there should be no charge. And that's what the Dirac Delta functions allow you to model. In 3 space, if you take away one of those Dirac deltas, now you're dealing with a line of charge. Take away 2 Dirac deltas, now you're dealing with a plane of charge. To make any of the other shapes or anything else you might want to work with, it's just a matter of setting up your integral and your bounds of integration. And through using that sifting property, it makes things so much simpler in evaluating that integration. Now, I know we talked just about modeling charge in this case. This should hopefully help you understand and figure out how you'll be able to model a lot of other things, not just in E&M, but in a lot of other fields as well, if you just need to localize everything to a single point in whatever dimensions you're working in. Anyways, thank you all very much for watching. If you have any questions, comments, or concerns, don't hesitate to let me know. So I will say thank you all again very much for watching, and I hope to see you all again next time.